And now in this lecture we'll find out the length of line segment AE. In the domain we have rectangle ABCD. We know that side AD of this rectangle is equal to 3 units in its length. In addition, we know that inside this rectangle we have those two semicircles. The radius of this big semicircle equals to 2 units. The radius of this small semicircle equals to 1 unit. Again, our mission is to find out the length of line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles are all right angles. So already know this angle is a right angle. This is also a right angle. This is a right angle. Finally, this is also a right angle. In the next step, we'll define the relevant points to this question with letters. We'll define the center of this big semicircle. This point is point P. Likewise, we'll define the center of this small semicircle. This point is point Q. We'll define the touching point of those two semicircles. This point is point S. We'll define the point of tendency of tangent AE in this big semicircle. This point is point L. And finally, we'll define the point of tendency of tangent AE with this small semicircle. This point is point G. In the next step, we will do a construction. That is to say, we'll extend line segment AE and side DC of this rectangle by a side line until they touch each other. So this is their touching point. We define this point. Their touching point is point F. So actually, F side DC, we extended side DC of this rectangle ABCD. So DC is one side of rectangle ABCD, therefore it is absolutely a straight line. Then by doing the construction, we extended the straight line DC by straight line, and the result is DF. When you extend a straight line by straight line, the result must be a straight line. Therefore, DF must be a straight line. So if we focus on the upper side of the straight line DF at point C, here the sum of the angles must be equal to 180 degrees. According to rule 3, that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line DF at point C? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the small right angle ECF, we define this angle EFC as alpha. So we will continue to focus on this small right angle ECF. In this small right angle ECF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we focus on the big right triangle, triangle ADF. On the big right triangle, triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha, according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. So we have here side DP, line segment DP equals to line segment PS. They are both, they are there on this circle, of this semicircle, that equals to 2. Therefore, the radius dp equals to 2 and the radius ps also equals to 2. Likewise, we have qs equals to qc, they are both the radii of this small semicircle, that is equal to 1. So qs equals to 1, qc also equals to 1. So here we have line segment CF. The length of line segment CF is unknown, so we define the length of this line segment CF as x. So we have the radius PL of this big semicircle, the radius PL that is equal to 2 is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. Whenever you have a radius that is drawn to the point of tendency, you can implement rule 1. So I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we also have here tangent AB that is tangent to this circle at this point, point M. In addition, we have the radius OM. The radius OM that is equals to R is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius PL of this big semicircle. The radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever your radius is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle. The radius QG is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever your radius is drawn to the point of tendency, then tangent AE will be perpendicular to the radius QG. If AE is perpendicular to QG, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. So, inside this small right triangle GQF, we have this angle that is equal to alpha, this angle that is equal to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So this missing angle must be equal to 90 degrees minus alpha. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we prove that this big right triangle LPF is similar to this small right triangle GQF. So I write it down. We prove that the big right triangle LPF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle PLF in the right triangle PLF, and it is equal to this angle, that's actually angle QGF, in the small right triangle FGQ. So again, actually found out that angle PLF in the big right triangle LPF equals to angle QGF in the small right triangle FGQ. They are both equal to 90 degrees and therefore they are equal to each other. In addition, we have this is angle alpha, that is a common angle that belongs to both triangles. So you can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha as it is belongs to the big right triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to this angle alpha as it is belongs to the small right triangle GQF, it will be defined as angle GFQ. So repeat again, we found out that here this equation means that angle alpha equals to itself. We just called to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle LPF. In the big right triangle LPF, and it is equal to this angle, that is actually angle GQF. In the small right triangle GFQ. So repeat again, we found out that angle LPF in the big right triangle LPF equals to angle GQF in the small right triangle GFQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we found out that all the triangles inside the big right triangle LPF are correspondingly equal to all the triangles inside this small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big right triangle LPF is similar, this is the sign of similar, to the small right triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LP in the big right triangle LPF over side GQ in the small right triangle GFQ equals to side PF in the big right triangle LPF over side QF in the small right triangle GFQ. Repeat again. We derive that side NP, the big triangle, or side GQ in the small triangle equals to side PF in the big triangle, or side QF in the small triangle. LP is the radius of this big semicircle is equals to 2 units over GQ. GQ is the radius of this small semicircle is equals to 1 unit, and it is equal to PF. PF in total equals to 2 plus 1 plus 1, that is 4 plus x. So PF in total equals to 4 plus x. Over QF. QF in total equals to 1 plus x. So if we found out that two equals to 4 plus x over 1 plus x. Here we'll multiply this equation by 1 plus x. And finally we get that two times 1 plus x equals to 4 plus x. Here we'll open the brackets on this side of the equation and we get that 2 times 1 is 2, so it is 2 plus 2x equals to 4 plus x. Here we subtract x from the equation and we get that here 2x minus x is x, so in total on this side of the equation we have x plus 2, that equals to 4. Here we subtract 2 from this equation and finally get that x equals to 4 minus 2 is 2. So if I found out that the length of this line 7 CF that is equals to x is equals to 2 units. In the next step, we'll prove that the big right triangle ADF is similar to this small right triangle ACF. So I write it down. We will prove that the big right triangle ADF, this big right triangle ADF, is similar to this small right triangle ACF. So write those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle ADF in the big right triangle ADF. And it is equal to this angle, this is actually angle ECF. And the small right triangle EFC. So I'll repeat again, if I found out that angle ADF with the big right triangle ADF equals to angle ECF with the small right triangle EFC, they are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. So if we relate to this angle alpha as it belongs to the big right triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself. So if we relate to this angle alpha as it belongs to the small right triangle ECF, it will be defined as angle EFC. So repeat again, this equation means that angle alpha equals to itself. We just want to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle DAF. In the big right triangle AFD, and it is equal to this angle, that is actually angle CEF. In the small right triangle EFC. So repeat again, if we found out that angle DAF in the big right triangle AFD equals to angle CEF in the small right triangle EFC, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually found out that all the triangles inside this big right triangle ADF are correspondingly equal to all the triangles inside this small right triangle ECF, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle ADF is similar. This is the sign of similar to the small right triangle ECF. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AD, the big right triangle ADF, over sides EC in the small right triangle EFC equals to side DF equals to side DF in the big right triangle ADF over side CF in the small right triangle EFC. So repeat again, we will derive that side AD in the big triangle or side EC in the small triangle equals to side DF in the big triangle or side CF in the small triangle. AD equals to 3 units over EC. EC is the missing side, so we leave it as it is. And this equals to DF. DF in total equals to 2 plus 2 plus 1 plus 1, that is in total 6. And 6 plus 2 is 8. So total DF equals to 8 over CF. CF equals to 2. So in total we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So I write it down. So if we found out that 3 over EC equals to 4. Here we multiply this equation by EC. And finally we get that 3 equals to 4 EC. Here we divide this equation by 4. And finally we get that the missing side EC equals to either 3/4 or 0.75 units. Repeat again, we have found out that this missing side EC equals to either 3/4 or 0.75 units. What is the length of side BC of this rectangle ABCD? We have the rule that states that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC. But AD is 3, therefore BC must be also equal to 3. So I write it down. If we found out that the missing side BC is equal to 3 units in its length. What is the length of this missing 9 segment VE? From the drawing, it is very easy to see that VE equals to BC minus EC. Again, BE equals to BC minus EC. So already known, if we found out that VE, the length of the missing 9 segment VE is equals to BC minus EC. So BE equals to BC. BC is 3 minus EC. EC is 0.75. So in total, BE equals to 3 minus 0.75. So BE equals to 3 minus 0.75 is 2.25. So if we found out that this missing 978 VE is equals to 2.25 units in its length. What is the length of side AB of rectangle ABCD? Again, we have the same rule that says that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So DC in total equals to 6, and therefore the opposite side AB must be also equals to 6 units in its length. In the next step, I'll copy this right green triangle ABE in a new page, and we implement the Pythagoras theorem on this right triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. So actually, this is the right green triangle ABE that I call it from the original drawing. I repeat again that side AB equals to 6 units in its length, side BE equals to 2.25 units, and the hypotenuse AE is the missing side. So according to the Pythagoras theorem, in this right triangle ABE, AE squared, that is the square of the hypotenuse, must be equal to AB squared plus BE squared. So I write it down. So AE squared equals to AV squared plus BE squared. Again, AE is the missing side, so we leave it as it is. So it is AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BE squared. BE is 2.25, therefore BE squared is 2.25 squared, is equals to 5.0625. So in total we found out that AE squared equals to 36 plus 5.0625 is equals to 41.0625. In conclusion, we found out that A is squared equals to 41.0625. Here we take a root out of this equation and finally get that the missing line segment AE, that is the line segment that we are looking for this question, is equals to the square root of 41.0625, and the square root of 41.0625 is 4.608. And this is also repeat again, the square root of 41.0625 is 6.408 units. And that is the answer to the question. We actually found out that the length of this line segment AE is equals to 6.408 units. Okay, so in the next step, I'm summarizing the lecture. In this lecture, we found out the length of this line segment AE. So in the drawing, we have rectangle ABCD. We know that side AD equals to 4 units in its length. Inside this rectangle, we have those two semicircles. The radius of this big semicircle is equals to 2 units. The radius of this small semicircle equals to 1 unit. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles are all right angles. In the next step, we define the relevant points to this question with letters. We define the center of this big semicircle. This point is point P. We define the center of this small semicircle. This point is point Q. We define the touching point of those two semicircles. This point is point S. Likewise, we define the point of tendency of tangent AE with this big semicircle. This point is point L. And finally, we define the point of tendency of tangent AE with this small semicircle. This point is point G. In the next step, we did the construction. That is to say, we extended line segment AE inside DC of this rectangle ABCD by side line until they touch each other. This is their touching point. We define their touching point. This point is point F. We know that DC is one side of rectangle ABCD, and therefore DC must be a straight line. Then by doing the construction, we extended the side line DC by side line, and the result is DF. The result is DF. So when you extend the side line by side line, the result must be a straight line. Therefore DF must be a straight line. So if you focus on the upper side of this side line DF with point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that said that the sum of the angles from one side of the side line is equal to 180 degrees. So which angles we have the upper side of DC, the upper side of DF at point C. We have this angle that is right angle plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the small right triangle ECF, we define this angle EFC as alpha. So, in the small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing third angle must be equal to 90 degrees plus alpha. Why? Because 90 degrees plus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees plus alpha according to the sum rule that says that the sum of the angles in any triangle is equals to 180 degrees. Okay, so here we have PD equals to PS, the above the area of this big semicircle. that is equal to 2. So PD equals to 2 and PS also equals to 2. Likewise, QS equals to QC. They are this small semicircle is equals to 1. So QS equals to 1 and QC also equals to 1. Here CF is the missing line segment, so we define the length of this line segment CF as x. Again, CF equals to x according to our definition. We have here the radius PL of this big semicircle is known to point L, that is the point of tendency of tangent AE with this big semicircle. Whenever your radius is known to the point of tendency, then tangent AE will be perpendicular to the radius LP according to rule 1. If AE is perpendicular to LP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius GQ of this small semicircle. The radius GQ, radius QG, is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. So in the small right angle GQF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this Fred-Vinson angle must be equal to 90 degrees minus alpha, according to the same rule that said that the sum of the angles in a unit angle is equal to 180 degrees. Likewise, in the big right angle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this Fred-Vinson angle must be equal to 90 degrees minus alpha. In the next step, we proved that this big right angle LPF is similar to this small right angle GQF. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we should prove that all the three angles inside this big right angle LPF are correspondingly equal to all the three angles inside this small right angle GQF. And therefore those two right angles are similar to each other according to angle similarity rule. So repeat again, we should find out that the big right angle LPF is similar to the small right angle GQF according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side LP in the big right angle LPF over side GQ in the small right angle GQF equals to side PF in the big right angle LPF over side QF in the small right angle GQF. Okay, again, we derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP equals to 2 or GQ equals to 1 and PF equals to 2 plus 1 plus 1, that is 4 plus x. So PF in total equals to 4 plus x over QF. QF equals to 1 plus x. So in total, if we found out that 2 over 1 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x and finally found out that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation and finally found out that 2 times 1 is 2, so in total in this side of the equation we have 2 plus 2x equals to 4 plus x. Here we subtract the x from this equation and finally found out that 2x minus x is x, so in total in this side of the equation we have x plus 2, that is equals to 4. Here we subtract 2 from this equation and finally found out that x equals to 4 minus 2, that is 2. So this line segment CF is equal to x is equals to 2 units. In the next step, we proved that this big right triangle ADF is similar to this small right triangle ACF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles, so we can write out that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we shall prove that all the triangles inside this big right triangle ADF are correspondingly equal to all the triangles inside this small right triangle ECF, and therefore those two right triangles are similar to each other according to angle similarity rule. So repeat again, we shall find out that the big right triangle ADF is similar to the small right triangle ECF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AD of the big right triangle ADF or side AC of the small right triangle ECF is equal to side DF of the big right triangle ADF or side CF of the small right triangle ECF. So repeat again, we derive that side AD of the big triangle or side DC of the small triangle equals to side DF of the big triangle or side CF of the small triangle. AD is free, or EC. EC is the missing side, so we leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2 plus 1 plus 1, that is in total 6. And 6 plus 2 is 8. So in total DF equals to 8 over CF. CF equals to 2. So in total we can find out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So we can find out that 3 over EC equals to 4. Here we multiply this equation by EC and find out that 3 equals to 4 times EC. Here we divided this equation by 4 and finally found out that the missing side EC equals to either 3/4 or 0.75. Okay, this is the missing side EC. That is equals to either 3/4 or 0.75 units. What is the length of side BC of rectangle ABCD? We have the rule that says that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC, but AD is 3, therefore BC must be also equal to 3 units in its length. What is the length of the missing 97BE? The length of the missing 97BE will be equal to BC minus EC. Again, B equals to BC minus EC. So B equals to BC, that is 3, minus EC, that is 0.75. So in total, B equals to 3 minus 0.75. 3 minus 0.75 is 2.25. So we found out that the missing 97BE equals to 2.25 units in its length. In the next step, we found out the length of the missing side AB of rectangle ABCD. According to the rule that said that the opposite sides of rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2. So 4 plus 2 in total is 6. So in total, we found out that the missing side DC is 6, and the opposite side AB must be equal to DC, and DC is 6, and therefore AB must be also equal to 6 units in its length. In the next step, I copied this green right triangle ABE in a new page and implemented the Pythagoras theorem on this green right triangle ABE. This is the green right triangle ABE that I copied from original drawing. Side AB equals to 6 units in its length, side B equals to 2.25 units, and AE is the missing side. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle ABE is AE, and therefore the square of the hypotenuse is AE squared, and AE squared must be equal to AB squared plus BE squared. Again, AE squared equals to AB squared plus BE squared. AE is the missing side, so we leave it as it is. So AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BE squared. BE is 2.25, therefore BE squared is 2.25 squared, that is 5.0625. So in total, AE squared equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So in total, we have found out that AE squared equals to 41.0625. Here we took out of this equation and found out that the missing 97AE is equals to the square root of 41.0625. The square root of 41.0625 is equals to 6.408. So in conclusion, we found out that the length of this 9 segment AE is equals to 6.408 units. Okay, thank you very much.